Hi everyone. So we're gonna finish up chapter 10 today. This is the video for chapter 10, lecture 2. So if you guys remember, the last time we learned about Lewis theory and we introduced the electron dot structure, right? And then we went into an electron dot structure is used for ionic compounds, and then the Lewis structure um, was used for covalent compounds. And we did, structures with single bonds, double bonds, triple bonds. We went to expanded octet, incomplete octet, right? So now we're going to continue. There are a few more structures that I would like to show you. So this next one is called resonance structures. Okay. And the best way to explain that is let's just go with an example problem. It will make a lot more sense what resonance structures are. So let's do NO3 minus as our structure. You'll recognize that as the nitrate polyatomic anion, right? Nitrate, NO3 minus. So remember, first step we do is valence electrons. That's 5 plus 3 times 6. Sorry, right, 3 times 6. And then the negative sign means you got to add 1. Remember that, right? So the negative sign, you have to add 1. So that's going to be 18, 19, 24 valence electrons. Okay. Then the central atom, which one is going to be in the middle? Obviously nitrogen here, right? Furthest away from the noble gas. And then you're going to distribute evenly around the oxygens, right? There are 3 of them. Then next step is single bonds only. Okay. And I just use 6 electrons, right? By making the 3 bonds. So I have 18 electrons left. And how am I going to put those? 3 pairs on each of the surrounding atoms. Okay, and that's my 18, yeah? Okay, so everybody has, all the oxygens have octet because I made them have octet, but I need to check nitrogen, right? It has 2, 4, 6 only. Okay, so I'm gonna need to make a double bond in order for my nitrogen to have octet. Now, the question you could ask me is, well, which electrons should we use? What 2 electrons should we use to put down for the double bond? Well, it doesn't really matter, right? Each of these oxygen is all the same. So you can, let's say if you put it down like this, these 2 electrons down, and what you'll get is the double bond is between this oxygen and and the nitrogen. This oxygen is still single bonded, and so is the bottom oxygen is still single bonded. Okay, so now we have our octet, right? Remember, we always check for formal charge. So let's check this oxygen here. 1, 2, 3, 4, 5, 6. And it should have 6, so its formal charge is 0, right? Let's check this one. So again, oxygen should have 6. But this one has 1, 2, 3, 4, 5, 6, 7. So it has an extra. So if it has an extra electron, it's going to be negative, right? And then this oxygen is the same as this one. 1, 2, 3, 4, 5, 6, 7. So it's negative as well. And then we check the nitrogen. 1, 2, 3, 4. But nitrogen should have 5. Okay. So since it's missing 1, it's gonna be a plus. Okay. So if we check to see whether this is a good structure, obviously this is the best that we can do. Because if I move, if I try to make nitrogen 0 here, I would violate the octet if I move these 2 electrons there. So this is the best you can do with formal charge. Um, and if you add up all the formal charge, right, minus, plus, minus, and 0, you get a negative charge, which matches the negative charge here. So that's the rule, right? The sum of all the formal charges must equal to the charge itself, okay? So that's the best that we can get with NO3 minus. Right? But then you're like, well, we could have taken the 2 electrons from this oxygen, right? So if we had done that, we would get a double bond here instead. And also don't forget to put the brackets minus, right? Because it's showing the overall charge. Okay, so little corner bracket and put negative. Okay, and if we had chosen to move these two electrons, then the double bond would have been down here. And then these oxygens would still have 3 lone pairs. Okay. So any of these one structure is called a resonance structures. So we have 3 resonance structures total. And they're all true structures, okay? And the truth is that the two electrons doesn't just reside between this nitrogen and oxygen, it moves all around, okay? Because the electrons are constantly in motion, right? And so the 2 electrons actually get shared between the 3 NO bonds, right? So sometimes the double bond is here, sometimes it's here, and sometimes it's here. And they're all in resonance with each other, meaning together they make up the whole picture of NO3 minus. And we don't have a way to show that because electrons are constantly in motion, right? And this is a static picture. So that's why I have to draw 3 instances, right? To get the whole full picture. So in other words, you can say that this resonance structure is only 33.33% of the truth. This one is also 33.33%, and so is this one. Okay. So together, they form the whole structure, right? The true structure. As you can see, right? If you add these up, you get 100%, right? So in other words, what we can say is that a third of the time, the electron spends its time here. Another third of the time, the 2 electrons spends its time here. And another third of the time, it spends its time here, okay? Because it's constantly in motion, right? And the way we talk about this is that the electron is delocalized over the entire structure. And how do we know this? Well, experimentally, we know this because if you have a double bond is stronger than a single bond. So you should measure the NO bond as being shorter than the other 2. But we don't measure that. Experimentally, we find that all NO bonds are completely equal to each other. So that's how we know that it is these resonance structures, right? And so what happens is the 2 electrons get evenly spread over the entire structure so that all NO bonds are completely the same strength and the same length, right? So there is a way to try and represent the 3 resonance structures with just a resonance hybrid. As in just one picture, right? Because this is kind of tedious to do. So the resonance hybrid tries to overlay these on top of each other to get just one picture. So to draw the resonance hybrid, all you have to do is include the bonds, right? Just draw the skeleton, right? Which is the single bonds. They never move, right? There's always at least one bond between the nitrogen and the oxygen. And then observe which bond is it that moves around. It's this bond, right? It's one of the double bonds here that is moving around. So any position where there can be a double bond, you're gonna draw a dotted line, okay? The dotted line represents a partial bond, okay? Fractional bond. Meaning it's less than 1. The bond order is less than 1. Okay? But to really find what the bond order is, you can actually just observe. I have 1 bond that is being shared over 3 positions. So for this picture, this bond is equal to 1 over 3. Okay? 1 bond being shared over 3 positions. So if we want to know the bond order, BO, bond order of an NO bond, it would be 1 1/3. Okay, because there's the 1, right? And there's the 1/3. Okay, so this bond order has 1 1/3. This one has 1 1/3. And this one has 1 1/3 bond. Okay. Okay, so if you add it all together, what do you see? 4, right? And that's true. 1, 2, 3, 4, always 1, 2, 3, 4 in each structure. Okay. Okay, so from now on, when you guys are doing Lewis structures and you see that there's a possibility of having resonance structures, I want you guys to list out all the resonance structures, followed by the resonance hybrid. Okay, and again, the right resonance hybrid is just, you know, where the double bond can be, draw a dotted line, right? And then figure out also the bond order. Okay, bond order is just bond strength. Bond order of 1 means you have a single bond. Bond order of 2 means you have a double bond. Bond order of 3 means you have a triple bond, right? So then a bond order of 1 1/3 is what? It means that you have a bond that is greater than a single bond, but less than a double bond, which makes sense when you observe the resonance structures, right? Sometimes this bond is a single bond and sometimes it's a double bond, right? So that means that its actual bond value is going to lie somewhere between 1 and 2, okay? And how much exactly? 1 1/3, okay? Because they all share these 2 electrons, okay? All right, let's do another one. HCO2 negative. All right, let's count up the total number of valence electrons. That's 1 plus 4 plus 2 times 6. And then plus 1 because of that negative charge, right? So that's 13 plus 5 is 18 valence electrons. Carbon is going to be in the middle. We're going to have oxygen here, hydrogen here. Okay. Doesn't matter how you do it, right? Just spread it out. Single bonds. Okay. That's 6 electrons used. Now we got 12 electrons left. We're going to put 3 pairs on oxygen, 3 pairs on oxygen. Remember, hydrogen doesn't need it. It's already happy. I've used up my 12, right? Let's check whether everybody has octet. Oh, carbon does not, right? 2, 4, 6 only. So I'm going to need to draw a double bond somewhere. So I'm going to take the 2 electrons from the top oxygen, which now will give me this picture. Double bond to the top oxygen, single bonded to the right oxygen. Okay, so it'll look like that, right? And let's do formal charge. Hydrogens, obviously, there's its 1, so it's 0. Carbon needs 4 valence electrons, that's 4, right? And let's check to see how many is on this picture. 1, 2, 3, 4. So it needs 4, and it does have 4, so it's neutral. Then for the oxygen, 1, 2, 3, 4, 5, 6. Oxygen should have 6, so this is 0. This oxygen, 1, 2, 3, 4, 5, 6, 7. Oh, it has an extra, right? So therefore it's negative. So you can, as you can see, this is a good structure because most of the formal charge is 0 except for the oxygen, which is carrying the negative charge of that compound, right? So the negative charge has to be in there somewhere on our structure. So we know that's the right structure, but then we also realize there could have been another way to do the double bond. Therefore, you have a resonance structure. So you're going to use what we call resonance arrow, and it's just a double-headed arrow, as you saw in the previous example that we did, right? So use the double-headed arrow to denote that you have a resonance structure, and then draw the all possible resonance structures that you can have. So it'll be that, right? Brackets, negative charge overall. And that's it, right? I can't draw another resonance structure. So for this compound, there are only two resonance structures, which means this is 50% of the time where the electrons are, right? Where the two electrons are. And this is the other 50%. Okay. So two resonance structures total. Okay. Circle it. So I know you're telling me, you found all the resonance structures. There are only two. Okay. And then you go to draw the resonance hybrid. Remember, you just need the skeleton, right? So where the bonds are constant, are fixed, you draw those in. So there's always a single bond to hydrogen, oxygen, and the other oxygen. And it's the double bond, right? The second bond that flips back and forth. So where does it flip? Between here and here. Okay. Brackets, negative. Okay. And notice on the resonance hybrid, you don't have to show the lone pairs. Because on a resonance hybrid, the electrons are, in motion, so you can't show that on your piece of paper. So don't worry about it. Don't put in the lone pairs. Just put in the bonds. Okay. So this would be your resonance hybrid, and to figure out the bond order for the dotted bond, right? Think about how many bonds are being spread over how many positions. So we're just playing with one bond right now, right? And it can either be here or it can be here. So that's two positions. That's like saying I have $1, right? And I need to spread it over two friends. That means each friend gets what? 50 cents, right? So again, 1 over 2, 50 cents, right? Or a half, okay? So one bond over how many positions? 2 positions, right? Basically, how many resonance structure you have, right? That's the denominator, okay? And then one bond over 2. So 1/2, right? And then you have the one that's already there. So the total bond order for the CO bond is 1.5 or 1.5. So this bond is 1.5 bond. This bond is 1.5 bond. And it makes total sense, right? Because you have sometimes the double bonds here and sometimes the double bonds there. In fact, how much? 50% of the time. The double bonds here, 50% of the time, double bonds here, right? So you don't quite have a double bond with the CO, but it's more than a single bond, right? But it's less than a double bond. And since it's 50%, it's right smack in the middle. So the bond order is 1.5, right? 1.5 for this compound. All right, let's do one more, okay? Let's do HSO3 minus, or no, let's make it more interesting. Let's do HSO4 minus, be 1 plus 6 plus 4 times 6, and then the negative charge plus 1, right? Valence electrons. It's 32 valence electrons together, right? Sulfur is your central atom. And you're gonna put the oxygens around and then the hydrogen. Here's a note that you should remember. H for the polyatomics always attaches to the oxygen. Okay, so not the central atom. Okay, very important. Okay, remember that. every time you see a polyatomic, that proton in front is always attached to the oxygen. It doesn't matter which oxygen, okay, but do not make it attached to sulfur, okay? No. So now we do single bonds. I've used 10 electrons. I have 22 electrons left. So I'm going to put 3 pairs on these outer ones. That's 6 times 3 is 18 already. I have 4 left. So I'll just put it here. That's 2 pairs. And that's it for my electrons, right? And then I do formal charge, right? Well, I do octet first. Everybody has octet. Even sulfur has octet, right? 2, 4, 6, 8. But now, remember, I have to do formal charge. So I usually do it on the central atom just first right away. It'll really tell me whether I have the right structure or not. The central atom really wants to be 0, okay? So sulfur has how many valence electrons? How many electrons does it want? Let's look up at the group number, 6, right? It needs 6. Well, how many does it have in this picture? 1, 2, 3, 4. So it's missing 2, right? We're gonna try to get it down to 0 because right now it's not there yet. So I'm going to put a double bond down like that. That's gonna get me. I'm gonna do 2 because I need 6 there. If I just do 1, I only have 5 around sulfur. So I'm gonna put this one down as well. So we're gonna have a double bond here, a double bond here, single bond here, single bond here. Okay, brackets negative. Okay. Now let's check the formal charge again to see if we got it. Sulfur, 1, 2, 3, 4, 5, 6. Sulfur needs 6 and does have 6, so it's 0. Cool, we got it down to 0. That's your goal, right? Is to get sulfur down to 0. And then the oxygen here, 1, 2, 3, 4, 5, 6. It should have 6, so 0. This oxygen, 1, 2, 3, 4, 5, 6. Should have 6, so 0. This oxygen, 1, 2, 3, 4, 5, 6, 7. Okay, 7 is too many, right? It has an extra, so it's gonna be negatively charged. This oxygen, 1, 2, 3, 4, 5, 6. Great, that one's 0. And our hydrogen is also 0, right? 1. So looking at the formal charge, it looks great, right? Everybody is 0 except for one atom, which is oxygen. And it carries that negative charge because it needs to, right? The negative charge has to be somewhere in your picture. And that's perfect that it's on oxygen because oxygen is also the most electronegative atom, right? So remember on your sheet at the bottom, the steps for Lewis structures at the bottom, it says best structures have the most non-zero formal charges, right? Sorry, the least non-zero formal charges. And then if there is a charge, it should lie on the most electronegative atom. So out of all of these, oxygen is the most electronegative. Okay, so, and yeah, let me just quickly say what electronegativity is. So I don't think we went over that. Electronegativity is how prevalent an atom is at pulling electron density towards itself during covalent bonding. So when you have a bond like carbon and carbon, it's the same. They're going to share their electrons completely the same. But if you have, say, oxygen and hydrogen, oxygen is more dominant at pulling the electron density, the shared electrons towards itself. So we say that oxygen is more electronegative, right? It has more dominant pull, okay? And the way that electronegativity trend goes is you look at your periodic table, it increases as you go to the right, and it increases as you go up, okay, for electronegativity. Okay, so you can look at your periodic table, right? If you compare oxygen, sulfur, hydrogen, oxygen is going to be the most electronegative because it's most to the right, and up. So the negative charge should lie on the most electronegative atom because electronegative atoms want the electron, right? So we know that this is the right structure, and now we just have to think about resonance structures. So what can we do? Let's play around with the double bonds, right? They could be here, but they could have been here. So draw that resonance structure. Double bond here, double bond here, single bond here, single. Okay, and can you see one more, right? You can just kind of do all combinations of where the double bond can be. They can also be opposite, right? So we have a double bond on top, double bond on bottom, single bond over here, single bond here. Okay, and that's it. Okay. Notice that you do not try to put the double bond on this oxygen because this oxygen is not the same as these three, right? Resonance only works if the combinations are, on the same identical atom, right? You see that this oxygen is attached to hydrogen, so it's different than these. So if you try to put a double bond here, you're gonna screw up the formal charge of this oxygen. So don't do that, right? Notice that in all of these resonance structures, it has the same formal charge, right? Same configuration of formal charge, right? And so this is the only three that you can get. Then let's do the resonance hybrid. Just draw the skeleton first, right? All of them connected to each other, just the backbone, right, of the structure. And then notice where the double bonds can be. It can be here, it can be here, and it can be here. So you do dotted lines. Okay. So sometimes the double bond's there, sometimes it's there, sometimes it's there. That's what the dotted line means, right? To figure out the bond order for the dotted line, let's see. How many bonds are we playing with? Like how many bonds are being moved around? 2, right? These 2 bonds are just scrambling around over how many places? So 2 bonds over how many places? 3. 1, 2, 3. Right? You're just taking 2 bonds and you're like making all the combinations over 3. So the dotted line is now actually 2/3 of a bond. So the bond order for the SO bond is 1 plus 2/3. So 1 and 2/3. Right? Where does the 1 come from? Well, there was already a single bond there, right? There's a single bond here, single bond. So this one is 1 and 2/3. This is 1 and 2/3. And this is also 1 and 2/3. Yeah. So that's how you do it for resonance structures. All right. So the next example, we're also gonna practice some more resonance structures, and then I'm going to show you how formal charge is really going to play a great role in you guys deciding which one is your best structure, right? So the usage of formal charge is a must in every structure, right? And it's very important. So let's do an example where we compare NCO minus and NCS minus. Okay. Well, let's do NCO minus first before we do this one. So in NCO minus, let's say that, I didn't know that carbon is the central atom. So I'm going to try both, right? I know I give you guys a hint that it's, carbon because it's going to be leftmost of the periodic table of the noble gas. However, that's not always going to be obvious, right? So some structures, you're just going to have to try things out and see which one has the best formal charge, right? So that's what we're gonna do here, right? We're gonna have 2 scenarios where we have, different central atoms, and then we're gonna use formal charge to pick the better one. Okay. So valence electrons here, 5 plus 4 plus 6. That negative means to do a plus one. 16 valence electrons. Okay, so let's work on the left structure first. Okay, 4 electrons used. I got 12 electrons left. So I'm gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I've used all my electrons. 8 here, octet is good, but carbon needs octet, so I'm gonna do double bond there, right? Just to see. Okay, and then I'm like, okay, octet's good. Now we check for formal charge, right? Let's start with nitrogen. Nitrogen should have 5 electrons. And it has 1, 2, 3, 4, 5, 6. So it has an extra, so negative charge on nitrogen. Carbon should have 4 valence electrons. Does it? 1, 2, 3, 4. It does. It's gonna be 0. The oxygen should have 6 valence electrons. 1, 2, 3, 4, 5, 6. Right? And does it have 6? Yes. So that's 0 as well. Okay. Now, it may look okay for now, but let's really check. So let's go to Canvas. I'm going to show you guys that steps, right? Drawing the structure. If you look down here, it says the best structures have fewest non-zero formal charge. Okay, so in our structure, this is the best we can do, right? 2 out of the 3 atoms have 0 formal charge. Of course, 1 atom needs to carry the negative charge. So criteria 1 has already been fulfilled. Let's look at criteria 2. Formal charge values closest to 0. Okay, that means all of these, if you have a non-zero formal charge, it should be as close to 0 as possible. So that's true. This is just a 1 minus, so that's as close to 0 as you can get. And then the criteria 3, the negative charge should be on the most electronegative atom. Okay, so the negative charge here right now is on the nitrogen. Here's the problem. That's not the most electronegative atom, which is between nitrogen, carbon, and oxygen. Remember, look at your periodic table. It will be oxygen. So this is actually not your final structure, even though it looks really good, right? Formal charge is telling you this is not your best structure. So let's try to see if we can get the negative charge to go to oxygen. What can we do? You guys see it? How about if we move this pair of electron, this lone pair, to make a triple bond, and then we move this bond and make it a lone pair on oxygen? What we'll get is a triple bond between carbon and nitrogen that has 1 lone pair. And then we have 3 lone pairs now on the oxygen. Okay, everybody still has octets here. Okay, then let's check formal charge. Nitrogen should have 5 electrons. Does it? 1, 2, 3, 4, 5. Yes. So it's 0. Carbon should have 4 electrons. So 1, 2, 3, 4. And does it? Yes. So 0. And then oxygen should have 6, right? In this picture, it has 1, 2, 3, 4, 5, 6, 7. It has an extra. So yes, look at that. We've successfully made oxygen carry the negative charge, which it should because it's the most electronegative atom. So actually this right here, both of these can be considered resonance structures, but this one is more stable. Okay? So if you show me this one only, I wouldn't count it as the right answer because that one is the best structure. Okay. If you want to be more thorough, you can also say, actually, there are like 2 resonance structures. This one, since it's more stable, who knows, it maybe, if we measure it, it could be, 70% to 30%. It's not 50-50 anymore, right? They're not equal because this one is better, okay? But then you can draw the resonance hybrid for that. Here. Which would be like, Okay, looks like that. Negative. Okay, the reason being sometimes this is a triple bond and a double bond, right? And then sometimes the CO bond is a single bond and sometimes it's a double bond. Okay, so that would be your resin hybrid. You want to do the bond order, you have one bond over two position, right? You have this one bond just flipping back and forth. So what is going to be your bond order? 2.5, and this is 1.5. Okay, does that make sense? Right? Now let's do it for this one. Let's say if you thought nitrogen was in the middle. Okay. Still 4 electrons used, 12 electrons left. Right? And then let's do the double bonds like we did earlier. Now we have double bond here, double bond here. Okay, brackets negative. Let's do our formal charge. Carbon should have 4. And right now it has 1, 2, 3, 4, 5, 6. So that's a -2. Okay. For nitrogen, it should be 5 electrons per atom. 1, 2, 3, 4. So it's a plus, right? Because it's missing 1. Oxygen should have 6, and 1, 2, 3, 4, 5, 6. So it does have 6. So you're at 0. Okay. As far as best structures, let's see. Let's go back, okay? Fewest non-zero formal charge. Not looking so hot, right? Compared to the other one. Because it has 2 non-zero formal charge. And we have a really big formal charge. So criteria 2 is kind of bad too, because the formal charge should be close to 0. We got a -2. That's really far from 0, right? And then third, negative charge should be on the most electronegative atom. The most electronegative atom is the oxygen, right? Again, we can try to make it better. So let's try to make it as good as possible. We can put this down for triple bond, right? Move these 2 electrons to be lone pair, and we'll have single bond here, triple bond here, with 1 lone pair. Okay, let's see if this is better. Carbon should have 4. Right now it has 1, 2, 3, 4, 5. Okay, so we brought this down to a -1. That's better, right? It's closer to 0. Nitrogen is still plus, right? Because it still only has 4 around it. This oxygen now has 1, 2, 3, 4, 5, 6, 7. It should have 6. So it has an extra 1, so now it's negative. Okay. Okay, so negative, negative, and a plus is a negative overall. So now we've spread it like that, but none of these now have 0. Okay, but at least this one is not -2. So I would say this structure is better than this one. Okay. However, compare this one to that one, it's obvious that that is the right structure. So nitrogen cannot be in the middle. Okay. So I'm just really showing you a, cases where formal charge is the one that is going to determine, right, your structure. And this one has much better formal charge than this one here. So that's my suggestion is when you guys do these Lewis structures, sometimes it's not going to be obvious. It won't be obvious what atom is connected to what. Sometimes there's going to be, ambiguity. How do you get around that? Try multiple, right? Try a structure where you have this connectivity. Try another structure where you have this connectivity. Go all the way through and then pick the one with the better formal charge criteria, right? And it goes by those 3 criteria, right? Fewest non-zero, closest to 0 formal charge, and and negative charge must be on the most electronegative atom, right? Use those criteria to pick your best structure. Okay. All right, so that's it for all the structures that we're gonna draw, right? You guys know now how to draw Lewis dot for the ionic compounds, and then the Lewis structures for the covalent compounds, all different types, right, including resonance structures. Okay, so let's continue with the slides here. So remember, this is the theory, right? Lewis theory. Um, and we're going to compare now the theory to reality, right? So how does the ionic bonding model stand up to reality? So Lewis theory implies that the positions of the ions in a crystal lattice are critical to the stability of the structure. So ionic solids should be really, really hard because you have such strong attraction between opposite charges, right? Ionic bonding model says that, a metal will lose the electrons, the non-metal will gain it to become like the noble gas, right? To have an octet. And so then you have opposite charges that attract each other. And so you have a very strong attraction, right? Remember Coulomb's law? Q1 times Q2, right? So ionic solids are really hard. And this is true. In reality, ionic solids are that's why they're solids, first of all, right? And they're very, very hard. Lewis theory also implies that if the ions are displaced from their positions, you would have repulsive forces occur, right? Because the plus minus are right next to each other like this, right? Each layer of plus minus are repeating, right? In a 3D array. So if you strike an ionic solid, what happens is that you displace that pattern of plus minus, and now you have a plus and a plus, say, next to each other, right? When you strike it, and then a negative and negative next to each other. So what happens? It's going to crack. So that's why ionic compounds are so easily cracked, right? If you put pressure on it. So ionic bonding model also implies that the ions are locked in position. They cannot move around. So in the solid state, ionic compounds do not conduct electricity, right? Remember, to conduct electricity, you must have electron movement, right? And so in the solid state, the ions are not moving. However, when you dissolve it, then you can have the crystal lattice is basically disassembled, right, into ions, and so the electrons can move in those ions. So if you take a light bulb, for example, and attach it to two electrodes, if you put it into the solid ionic compound, it will not light. Okay. But now if you dissolve the ionic solid and you put it into the solution of that ionic salt, then you're going to get conductivity, right? You're going to get electricity, right? The more ions you have in solution, the brighter the bulb is going to be, right? So let's say if you have sodium chloride, you're only dissociating to Na plus and Cl minus. That's only two ions, right? And if you compare it to, say, calcium chloride, that's CaCl2. So now when you dissociate, it's Ca2 plus and 2 chloride minus, therefore 3 ions, right? That should light up the bulb more. So the more ions in solution, the higher the conductivity is going to be. Okay, so now let's see the model versus reality for covalent bonding. So Lewis theory implies that some combinations should not be stable, where others are stable. And this is due to, what we call the octet, right? And remember where the octet comes from is you have the noble gas having a configuration of S2P6, right? All of the S shell, subshell is filled. All of the P subshell are filled, and that's P6, right? And S2. So 6 plus 2 is 8. Okay, so what Lewis theory predicts is that, oxygen is going to be more stable when it is bonded to two other atoms. Okay, and not three, for example, right? If it's bonded to 3 atoms, then you're going to have an extra electron. So you're going to violate that octet. So that's why water is not H3O, but H2O. Okay. If you were to have H3O, then you'd have to have a cation because one electron has to get removed, right? To not violate that octet, right? So what that means is Lewis theory will predict that the melting and boiling points of molecular compounds are going to be low since you don't have charges, right? Remember, ionic compounds, you have plus and a minus attracting each other, but in covalent compounds, you don't have that. And so you're not going to have, melting points and boiling points as high as ionic compounds. And in reality, that's true. A lot of the molecular compounds have melting points that are generally less than 300 degrees Celsius, right? And so that's why you can find molecular compounds that are in 3 different states, right? You can find them as solid, liquid, or a gas. Okay, so what that means is that some molecular solids are going to be pretty waxy and soft, right? Not hard like the ionic compounds. Some can be brittle, some can be hard, but most are going to be, soft and waxy. Also, molecular compounds do not conduct electricity, right? Because you don't have ions in solution, okay? Okay, so let's move on to what we call bond polarity, okay? So bond polarity is measuring in covalent compounds, in compounds, how evenly the electron is being shared between the 2 atoms, okay? Now, most bonds have some degree of sharing and some degree of ion formation to them. And it's a whole spectrum, right? So you can have bonds that are equally shared, right? Where they equally share the electrons, but you can have bonds that where the electron sharing is so uneven that basically one atom is going to steal the electron from the other, right? And what does that sound like? It sounds like ionic bonding model, right? So, up until this point, we've, for the sake of simplicity, have said you either have ionic compounds or you have covalent, right? It was really binary. That's not true. Nothing is on the binary, as you guys have seen so far, right? Everything's on a spectrum. So even bonding models are on a spectrum. So if you have an ionic bonding model, you're at the other end of the spectrum where there's no sharing at all, right? And then the other end of the spectrum is completely equal sharing, right? And to determine whether a bond is polar or not, and we're to classify whether it's ionic or covalent, we're going to use electronegativity as a measure. And I've already explained to you guys briefly, right, what electronegativity is. It's the ability of an atom to attract the shared electrons toward itself. So how, prominent or how dominant the atom is at attracting electrons to itself. So the trend goes, it will increase as you go across the period and increase and decrease as you go down the group, which means that fluorine is the most electronegative element and francium is going to be the least electronegative element, okay? So here's our scale, right? Here's the periodic table. These numbers represent electronegativity. You see that by far fluorine, right, is the most electronegative at 4.0. Looks like oxygen is the next one at 3.5, okay? Francium and cesium are the least electronegative, right? Because it's on the metal side, right? Metals don't want electrons. That's kind of how I think of it, right? So it's not electronegative, okay? So just 0.7. Okay. So when you think about bond polarity, what you're thinking about is how different the electronegativity between the 2 atoms are. If they are completely equal, then you have equal sharing, okay? But if you put, say, fluorine and cesium together, well, the fluorine is going to hog all the electrons because it's more electronegative, right? And in fact, it hogs it so much that the fluorine just steals the electron from cesium, okay? Because their electronegativity difference is so big. So that's really all you're looking at is their difference in the electronegativity to figure out where it is on the spectrum, okay, of bond type. So there is a spectrum, and I like this picture the best, okay? So you can see clearly where we kind of set the boundary. Remember, this is kind of arbitrary. We're just doing this for, simplicity of how we think about bond type. But, this is just a whole spectrum, right? This is how nature is. So if you have something that is purely covalent bond, that means that it's non-polar, okay? So the electrons are shared more or less equally, and they will have an electronegativity difference of 0.4 or less, okay? Between 0.4 and 2 for the electronegativity difference, that's where the electrons are shared unequally. So one atom will dominate over the other. So notice how we denote that? Delta minus versus delta plus. So this atom on the left is more electronegative, so it pulls the shared electrons towards itself more, and so you can think of it as partially negative. Remember that delta means partial. So it's not a real charge, right? Or it's not a full charge, but you can think of it as partially charged, right? Partially negative. And the atom on the right is feeling rather delta positive, right? It's feeling a little positive because it got the electron density stolen from it, right? A little bit, okay? Now above 2, that's how we think of ionic bonding. Is now the electrons aren't even shared anymore. The difference in electronegativity is so large that you don't think about it being shared. It's one completely stealing the electron of the other, so that you have fully charged ions, right? So the left one takes the whole electron, and the right one lost the whole electron. So you have now a fully negative charge and a fully positive charge, okay? So you see what I mean, that this is a whole spectrum, right? Where you start at 0 and 0, more or less neutral, right? So you don't have a polar bond. That's why it's called nonpolar. And then here you have what's called polar bond, right? Unequal sharing. And then ionic bond. This is a superpolar. It's very, very polar, right? It's so polar that it's called ionic, right? So that's how it works. And when I ask you on the test, right, to classify a bond type, I will give you the electronegativity value. I will either ask you, or give you the electronegativity value if I'm asking you to calculate the actual number. But most of the time you can just eyeball it, right? So remember that electronegativity increases as you go to the right and as you go up. So the more farther the atoms are diagonally to each other, it means, the more polar you are, right? Okay, so let's do some examples here. So when you have HF, right, you're going to have unequal sharing. Obviously, you look at H and F, right? F is 4, H is 2.1, okay? So F is going to hog the electron, and I want you guys to be able to understand these notation as well. Find the more electronegative atom and put delta minus. The other one gets delta plus. And then also, you should be able to draw the bond polarity arrow on the bond, okay? Make sure that it's parallel to the bond. The arrowhead should point towards the electronegative atom. And then you see the butt of the arrow, make a little hash mark like this, make a vertical line so that the butt looks like a positive, right? So fluorine is more electronegative, hydrogen is more electropositive, right? And also hydrogen is carrying that, partial negative charge, and fluorine is carrying a partial, right, a delta minus, okay? So that's how it works, right? Because fluorine is more electronegative. So we would say that this is a polar bond. Okay. Now, you can actually measure the bond polarity of a bond. And we've done that. It's called a dipole moment, mu. Okay. Mu is Q times R, and it's measured in dBi, or capital D. Okay, so if you look at Cl2, for example, since you have two exact same atoms, the delta En is 0, so your dipole moment is 0, right? But if you look at ClF, right, you have 0.88, and then lithium and fluorine, well, lithium is a metal, right? So really low electronegativity. Fluorine has the highest electronegativity, right? So their difference is 3. So remember how that spectrum goes, right? 3 is over here. We got an ionic bonding situation, and the dipole moment is really, really high. Okay. So the higher the dipole moment, right, the more unequal the sharing is. And that's based on the difference in electronegativity. All right, so the percent ionic character is then the percentage of a bond's measured dipole moment compared to what it would be if the electrons were completely transferred. So in this graph right here, you can see that even the most ionic compound that we, can think of, right? I always use the example, of sodium chloride or even like potassium fluoride, lithium fluoride. None of those are actually 100% ionic character, even though that's, what we think of when we think of ionic compounds, right? It's metal, non-metal. But this points to that there's a spectrum, right? So even the most ionic compounds have some degree of covalency, right? So you can also see here, even the HCl, right? Those are two nonmetals. Even nonmetals have ionic character as well, right? HCl is having about 23% ionic character, because remember, it's like proton, H plus, and Cl minus, right? And so this really shows you that these bonding types, we've been just simplifying it so far, right? When it's actually really on a spectrum. And it's a little bit more complex than how we teach it in Gen Chem, right? So let's do some example problems now, so that we can classify, whether a bond is covalent, polar covalent, or ionic. Okay, so let me write these on the board and then we'll do it together. Okay, so the first one, A, is between strontium and fluorine, right? So you just go to the that one periodic table that lists the electronegativity values. This one, right? We look at strontium, which is 1.0, and fluorine is 4.0. And then to take the difference, all you got to do is take the bigger number, subtract the smaller number, right? So the difference, remember, delta is difference in electronegativity is 4.0 minus 1.0, which is 3.0. And then if you guys remember that spectrum, right? 3.0 falls in the ionic regime, right? So we can classify the bonding type between strontium and fluorine to be ionic, okay? You should memorize this continuum. It's easy. Just remember the two numbers here, 0.4 and 2, right? So less than 0.4, you're at nonpolar. And then between 0.4 and 2, you're at polar covalent. And then above 2, you're ionic. Okay. Okay, so let's do the next one. The next one, B, is between nitrogen and chlorine. So if you look at nitrogen, we're at 3. And chlorine is at 3 as well. Okay, that's pretty obvious, right? They're both the same electronegativity, so 3 minus 3 is 0. So we don't have polarity, right? It's a non-polar bond. We say non-polar. Okay, let's go to nitrogen and oxygen. So nitrogen was 3. Oxygen is 3.5, right? So what is the difference? 3.5 minus 3, which is 0.5. 0.5 is greater than 0.4, right? So we are in the polar region. Okay. All right, so let's also practice putting in delta positive and delta negative and also the polarity error. You'll need to do that in the later chapter. So if you have an NCl bond, right? Now, you don't need to do that for ionic because it's there's no covalency, right? So for NCl, since it's covalent bond, then you can say this is delta negative. Wait, so actually this one is 0, so we don't even need to draw for that, right? It only matters for one that is polar. So for non-polar and ionic, you don't have to worry about it. But when it's polar, then remember that more electronegative atom gets delta minus, and the less electronegative atom gets delta plus, okay? And then as far as bond polarity arrow, it points towards the oxygen, right? And then make that little vertical so that the butt of the arrow looks like a positive, right? So that matches, okay? So anytime that you're, analyzing a bond, right? You want to be able to do that, right? Assign delta positive, delta negative, and then draw the bond polarity arrow. Was that problem that we were working on? Here we go. So let's keep going. I and I. CS and BR. And P and O. Okay. So we go to, well, I and I is obvious, right? It's the same atom. So delta EN is going to be 0. That's going to be non-polar. Okay. Now we go to CS and BR. CS is 0.7 and BR is 2.8. So delta EN is going to be 2.8 minus 0.7, which is 2.1. So you go down to this spectrum, right? Over 2 is considered ionic. And then the last one between phosphorus and oxygen, so we look up phosphorus, is 2.1. Oxygen is 3.5. So the delta EN there, 3.5 minus 2.1, which is 1.4. Okay, 1.4 is below 2, but above 0.4. So this is a polar bond, right? We have unequal sharing here. And so let's draw that bond. And which atom should get the delta minus? It'll be the oxygen, right? Because oxygen's more to the right and up than phosphorus. And phosphorus get delta plus. The direction of the polarity arrow will point towards the oxygen, right? And then we have that little plus butt of the arrow pointing towards phosphorus. Okay. Okay. Okay, one of the last topics here we have for this chapter is on bond energies. So bond energy is like how it sounds, right? Energies are stored in the bond. So if you want to break the bond, it's an endothermic process, right? Because you have to go in and break the bond. So it's defined as the amount of energy it takes to break 1 mole of a bond in a compound in the gas state, okay? And the breaking of the bond will be homolytically, meaning each atom gets half of the bonding electrons, right? So of course, it's always going to be breaking is always going to be endothermic. So the bond energy is always going to be a positive number. Okay. So then when you're trying to figure out the enthalpy of the reaction, you can use bond energies to figure out what the cost of breaking bond is, and then what you get back from bond making is, and then you can get enthalpy of the reaction, right? So this is, I guess, another way that you can think of doing Hess's law, right? By using bond energy. So let's look at a few bond energies. you have C triple bond C here compared to a C double bond C and a C single bond C. Notice that it takes more energy, right? 837 kilojoules to break a triple bond than it does a double bond or it does a single bond, right? Which makes perfect sense, okay? Here we can compare C triple bond N to C double bond N and C single bond N. Again, you see that, you know, a triple bond's stronger, right? And so you're going to take more energy to break that bond than, say, a CN bond. So in general, what you can say is that a shorter bond is a stronger bond. So triple bond is the shorter bond, right? Because it's higher in strength. So the shorter the covalent bond, the stronger that bond is. So if you look at BRF, BRCL, and BRBR, remember that here in each case there's a BR, right? But what's different is the fluorine, the chlorine, and the bromine. That means that as you go down a group, right? Fluorine, chlorine, bromine is in the same group. As you go down the group, remember that the atoms get larger. And so the bond distance is going to be increasing here, right? So BR bond distance is going to be higher than BRCL, which is higher than BRF. And notice that's why the BR bond has the lowest bond energy, right? Because it has the weakest bond. Right? Well, bonds will get weaker down the column, right? But bonds get stronger across the period. Right? That's how it goes. So you will have this table, or I'll give you the values on the exam. You don't have to memorize these. Just notice, you know, what units they are. It's kilojoules per mole here, right? So you will have to multiply by, you know, the number of moles to get that energy. So just to break one hydrogen-hydrogen bond, right? 1 mole of hydrogen-hydrogen bond, then it'll take 436 kilojoules. Of course, if you're trying to break 2 hydrogen bonds or 2 moles of hydrogen bond, then it will be double this number, right? So yeah, you can see here, right, that everything is tabulated for you. And there's only one more thing to note. See that C double bond O has a little asterisk by it. To break the C double bond O, it's going to take you 736 kilojoules per mole. But in CO2, it costs a little bit more. So if you're doing CO2, make sure that you're using the number 799 rather than 736. Okay, so how are we going to use bond energy to estimate the enthalpy of a reaction? It's really easy. You just count, right? When you, in the reactants, you have to break the bonds. And in the products, you have to form bonds, right? So the reactants have to break their bonds. That'll be a endothermic process. But in the reactants, when new bonds are formed, that's actually an exothermic process. And so that's why all you have to do is go break minus make, right? Because break has to be positive number because it's an endothermic process. Making bonds is an exothermic process, right? You get the energy back. So that's why it's minus make. So that's all you have to remember is go break minus make in order to find the enthalpy of a reaction. So let's do this one together. So what we have here is CH3, CH4, sorry, plus Cl2 goes to CH3Cl. And here it already has the structure for you, right? So I'm just going to copy that down. For these problems, you always need to start with the structure. So if this hadn't given you the structure and it only gave you chemical formula, then you have to draw the Lewis structure, right? That's why we learned that already. So draw the Lewis structure of each reactant and each product. Okay. And then you go and you look at the bond energy, right? So this is what I got, right? CH4 plus Cl2 goes to CH3Cl plus HCl. And I want to make sure I have the correct Lewis structure. Okay. Then I can go and figure out what bonds are being broken and what bonds are being formed. Okay. So think of it as like, you know, you're building Legos, right? You're trying to build something new from something that's existing. You may have to take apart that piece and then put together these pieces. So that's all you're analyzing here. Look at the left side and the right side, what's being broken and what's being formed. Well, here you started with CH4 and you end with CH3Cl. That means you have to break a 1 CH bond. Okay, so I make a table, break. Okay, 1 CH bond. Okay, and then what else? Well, I see on the right side the chlorines are separated, so that must mean I also have to break 1 CCl bond. Okay, and then that's it, right? That's it. I don't have to break anything else. But over on the right side, I'm gonna do a make column, right? So what bond is being formed on the right side? Well, you broke the CH bond to form a new what? CCl bond. So 1 CCl bond is being formed and 1 HCl bond is being formed. Okay. So now that you have that, you go to your bond energy table, right? And you tabulate. To break 1 CH bond, that's 1 mole times 436. CH is 414. Right, kilojoules. Right. And then you break 1 ClCl bond, which is 243 kilojoules. Then on the right side, you make 1 CCl bond. So where's the CCl bond? $339 kilojoules. And then you make 1 HCl bond, which is 431. All right, and then so you just sum it up. What's the total for breaking? All right, just sum it up. Total for breaking is 657 kilojoules. Okay. The total make bond is 770 kilojoules. Okay. And then remember how it goes. Breaking is endothermic, so it's positive. Making is exothermic, right? So when you break a bond, you require energy. But when you make a bond, you get energy back. So energy comes out. So this will be break minus make, which means you also do 657 minus 770. So your enthalpy of the reaction is negative 87. Nope, sorry. 3, 1, 1. Right? Negative 113 kilojoules. Okay. So overall, it's an exothermic process, right? For this reaction. Okay. And we did this using bond energy. Remember in chapter 7, we had used products minus reactants, right? In a previous chapter, we took enthalpy of the formation, added together products minus reactants, right? So here we're calculating the same thing, but we're just using a different method, which is called bond energy, right? So just read the problem carefully, right? And look at what they give you in order to figure out what the enthalpy of the reaction is. Okay, let's do another one together. Hydrogen gas, a potential fuel, can be made by the reaction of methane gas and steam. CH4 gas plus 2H2O gas goes to 4H2 gas plus CO2 gas. Use bond energies to calculate the enthalpy for this reaction. All right, let me write it down and then we'll do it together. First step always, right? When you do this with bond energy, you need to know the bonds. And here, it's not showing you the bonds, right? It's only showing you the compound. So that's why you use your Lewis structure steps You know how to draw Lewis structures now to draw CH4. I'm going to do it fast, right? Because we've done a bazillion Lewis structures. You guys know how to do this now. That'll be CH4, right? And plus 2 water. Water is going to be like that, right? And there's 2 of them, right? And then 4 H2, so 4 H2, right? That's easy. And then CO2, 1 CO2. Carbons in the middle, got double bonds to the oxygen. Each oxygen has 2 lone pairs. So as you can see, always start out with the Lewis structure, right? Okay. And then do your break and make table. Okay, let's see. From CH4, where's my carbon over here? I had to break all the carbon-hydrogen bonds. So how many is that? 4. Okay? Because the carbon over there is not attached to any hydrogen. So that means all the CH bonds have to be, were broken, right? And what about the water? Well, look, the water is not also attached to any hydrogen on the right side. That means all of the water, the OH bonds in water break. There's 2 OH bonds per 1 water, but there's 2 waters. So that's 4 OH bonds being broken. Right? Makes sense, right? Now you go to make. What are we making? Oh, there's a new bond that forms as HH. How many? 4. Right? So look at the coefficients too, right? And then we have 2 C double bond O form. Okay. But this is in CO2. So we want to make sure we grab the right number. If you remember, it was a different number for CO2. So there we go. Let's get the numbers down. So CH bond is 414. But we have 4 of them. So we're going to do 4 mole times 414 kilojoules per mole. Okay. And then for OH, it's 464, as you can see. And there's 4 of that. So 4 moles of 464. So 4 times 464, right? Make sure you pay attention to the coefficient. And then 4 hydrogen. So it's going to be 4. On the mix side, 4 mole times 436. For CO2, or for the 2 of the C double bond O, you're not going to use 736, right? Because we are at CO2, so it's going to be 2 mole times 799 kilojoules per mole. Okay. And there we go. Okay, we just have to now evaluate, right? 4 CH bonds break, so 4 times 14, 414, I mean, is 1656 kilojoules, right? See moles cancel. And then 4 OH bonds break. So that's 1856 kilojoules. Okay. And over here, make 4 HH bonds, so 4 times 436. That's 1744 kilojoules. And then 2 moles times 799 for the 2 C double bond O bonds that form. That's 1598 kilojoules. Now we sum everything up. You get for the mix side, 3342 kilojoules. On the brick side, we get 3512 kilojoules. Okay. And remember how it goes. Break minus make, right? Just have that mantra in your head. Break minus make, break minus make. So break minus make, 3512 minus 3342 give you 170 kilojoules. Okay. Positive number, so your enthalpy of reaction is positive overall, and that is an endothermic reaction, right? Because it requires 170 kilojoules of energy. Okay, let's see if we got that right. Yep, there we go. Okay, so there are more practice for you guys here. Make sure that you do it. Right? There's definitely going to be a problem like this on the exam. It's you know, maybe even a couple problems, right, where you calculate enthalpy of reaction from bond energies. Okay, let's go through these last slides. We're almost done with the chapter. Let's talk about bond lengths, right? So what determines bond lengths is a couple things. The size of the atom, right? And it correlates to strength as well. So if you look at these diatomic elements, F2, Cl2, Br2, and I2, notice that I2 is by far the longest bond distance, whereas F2 is the shortest. It correlates to size, doesn't it? Because think about it. If you have two small people hugging each other, they can hug each other much more tightly than, say, two larger people, right? They won't be as close to each other. So bond distance is going to be longer for atoms that are larger, okay? And it's going to be shorter for atoms that are smaller. But this also correlates to bond strength, okay? So if you have two small people hugging each other, they can hug each other tighter, right? So it's a stronger bond than if you say you have, you know, two bigger people, they wouldn't be able to hug each other as tightly, right? So it's going to be um, not as strong, right? So there you go. The shorter the bond, then the stronger the bond. Okay, the longer the bond, the weaker the bond, right? Okay, so here you see that. Let's look at carbon-carbon bonds. Notice that the shortest bond is a triple bond, right? 120 picometer versus a carbon single bond is 154 picometer, right? So since carbon single bond is less strong than a triple bond, it's also longer, right? So that's the association that you want to make. Is that a longer bond is a weaker bond, and a shorter bond is a stronger bond. Right? Okay, we're gonna stop there. That's all of chapter 10. So I'm gonna see you guys next time for chapter 11.